everybody. We are very happy to have Professor David Coit with us today. The title of the seminar is Economic and Resilience Data for Adding Battery Capacity to Photovoltaic Array Generation. So Professor David Coit is a professor in the Department of Industries and Systems Engineering at Rutgers University. His current teaching and research involves system reliability modeling and optimization, and energy systems optimization. His research has been funded by National Science Foundation, U.S. Army, U.S. Navy, industry, and power utilities. He has over 110 published journal papers and over 90 peer-reviewed conference papers. He has been awarded several NSF grants, including a career grant from NSF to develop new reliability optimization algorithms considering uncertainty. And he is the recipient of several prestigious awards. I have the laundry list here. I'm not going to read the whole thing. So he received his bachelor degree in mechanical engineering from Cornell, MBA from RPI, and MS, and the PhD in industrial engineering from the University of Pittsburgh. So we're very happy to have you here. And
thank you very much. It's very much a pleasure to be here. This is my first time to Texas Tech. And although it's my first time here to Texas Tech, I do know some of the faculty. In fact, the Department Chair Brian Norman. I met him in 1995, I think, plus or minus. Yeah. We were both young children. No. I was finishing my PhD at the University of Pittsburgh, and they invited this young guy at the time in for a job interview. Must have gone well. He got the job. So let me start like I always do. I'm from Rutgers University. I'm going to hope everyone in here knows what Rutgers University is. I suspect, however, some might not. So just very quickly, Rutgers is the 8th oldest university or college at the time in the United States. We're a huge public university. We're the State University of New Jersey. We're one of the largest universities in terms of enrollment in the Northeast USA. Here's the main campus where I work right here, Rutgers, New Brunswick, situated between New York and Philadelphia. We're now, for the last 3 years, a member of the Big Ten football conference. So we play Ohio State, Michigan, Wisconsin, Nebraska. We don't beat any of those teams, but we do in fact play them. And if you're interested in a nice piece of trivia, and you can look this up, it's true, is the first college football game ever played, ever, was in 1869, and it was Rutgers against Princeton on the Rutgers campus. We have a statue. So Rutgers won that game. Still looking for the next big victory. Okay, quickly, here's the research I do. For 20 years, since I've been a professor, and Professor Xiang explained some of those publications and things, my research has been system optimization. And generally that means system reliability optimization. So complex system, often with a stochastic objective function, that are difficult to solve. And so many of my recent research papers have been when the components within the system are degrading, but the degradation paths are probabilistically dependent, which doesn't always happen, but happens often enough, and the current models don't cover that. I have a very good publication with Professor Yisha Xiang, I guess that when it first came out, for months it was the most downloaded publication for IIESE, so she makes me look good. About 10 years ago, I got a phone call in my office from a gentleman from the Canadian Power Company. And he said, and this is pretty much accurate, so he works Canadian Power Company up in Toronto, the electrical power grid, and this would be the distribution, in other words, the final stage of the power grid that's coming into your home or this building and things like this. He said to me, Professor Coit, I've read your paper. He was referring to a paper I wrote on multi-state reliability systems, where you had multi-state components of a multi-state system. This was a paper with Jose Ramirez Marquez. And he said, I read your paper, and as a professor, those of us who are professors know we're never quite sure. He said, I read your paper, and it's of no value to me. I said, okay, thanks for the feedback. He said, however, if I gave you a small, well, he didn't use the word small. If I give you a research grant to fund you, it might in fact be of value to me. So I said, okay. And that started about 10 years ago, my work in complex system reliability. The system became originally the distribution system, the final stage of the electrical power grid, generation, transmission, distribution. But then later it expanded to transmission and generation. Originally, all my work was focused on reliability of those systems. But then we actually even took the reliability part out of it. Some of my recent research projects has to do with expanding the power grid to minimize CO2 emissions, giving an objective function with healthcare costs, which can't be estimated except for through a simulation model, things like that. We had Hurricane Sandy in New Jersey several years ago. And I don't know, it wasn't just New Jersey, it's everywhere. The emphasis seemed to shift, but for us in New Jersey, Hurricane Sandy wiped out, there's towns along the ocean that haven't recovered. The issue switched from reliability to resiliency. And so resiliency, there's different metrics with that, but it's the ability to respond effectively and in a time-efficient manner to some extreme event, whether it be a hurricane or a tornado. So this gentleman here, Dunbar Birnie, he's the Rutgers expert in a PV, photovoltaic arrays, among other things. He's in the material science department. He asked me to start to work with him. And so we have, today's talk is something that's new for me. It's not something, as she said in the introduction, I've been working reliability many years. This is something that's just within the last year or so. So this talk today, though, has to do with resiliency. And if some critical asset, hospital, manufacturing facility, a school, which is connected to the power grid but becomes disconnected from the power grid due to some extreme event and operating in an island capacity, how we can continue to meet the demands for electricity given the uncertainty of when this extreme event, when the power will be restored. So that's today's talk. These are the two students who work with me, Xhou and Stamatis from Greece. And I need a better picture, I think. So the work we've been doing at Rutgers with a combination of those four gentlemen, and Rutgers also has a SEEP Center, part of our Blaustein School of Planning and Public Policy. The SEEP Center is the Center for three E's: energy, environment, and economic policy. They've been the ones who have given us funding, and they've been the ones that have been giving us problems to study. And so the research objectives, and I've got now both of those PhD students working in this area, and just quickly, this is overall objectives, is optimization models, often stochastic optimization models for the some aspect of the electrical power grid. So constant improvements make it more resilient, more reliable, cost effective. We have a major emphasis, it's not today's talk, on cascading failures, generally with a transmission system, when one failure may lead to another, which leads to another, which leads to another. Most of our reliability models, even the ones that don't require independent failure time distributions, do not handle that, although other people have researched that. So we've been doing a major emphasis on cascading failures, and at the same time, we're doing work where we have constraints to introduce renewables. Wind, like you see in Texas. I drove here yesterday from San Marcos, where Texas State University is, so it's about almost a 7-hour drive. So I passed, I was counting, I think 1 million wind turbines, maybe more. More specifically, these are some of the research papers we have written. Our goal, improve resiliency and reliability, minimize carbon emissions, mostly CO2, but also CO, integrate renewables, minimize total costs. These are some of the papers. We have a very recent paper, Reliability Engineering System Safety, and a very good paper, I mean it's my own paper, stochastic optimization for generation expansion given climate change. But today's talk will be on this research paper, 2019, economic value of adding batteries to the PV array. So just for a problem domain, the electrical power grid, I'm from New Jersey. We usually, for our problem application area, we consider the Northeast USA. But we have the electrical power grid. If we look nationally anyways at the generation of electricity, I mean, every state is different, and the rules and regulations vary state by state. My state, New Jersey, we have 3 big nuclear power plants in South New Jersey, but there's no more burning coal. We burn mostly natural gas. But I lived in Pennsylvania, of course, where that's going to be a hard sell. But burning coal is still very important, and just south of there is West Virginia, even more so. But we focus in on solar, is 6%. .6, I don't know what's right. I guess I'm missing a point. So why? Well, lots of reasons. Lots of reasons. Not cost effective probably right now. Manufacturing barriers. Other reasons. One of the most common reasons, and you may say, well, of course, I knew this already, is it's not sunny all the time. In fact, it's not sunny at night ever. And for something like the application we're looking at, where the system is getting disconnected from the power grid due to an extreme event, the generation of electricity from an asset that can only be used during portions of the day, and even then only when it's sunny, is a problem. So new solutions, new materials can make this more cost effective, efficiency can go up, but my talk today is the third one that's in bold. If we can combine something like a PV array that during normal usage feeds into the power grid, but during some event such that the system gets disconnected from the power grid operating in island mode, the PV array, which by itself cannot meet the demand, but if it's married or paired with battery capacity that's being charged when it is connected to the power grid, when it is sunny, can make solar and PV photovoltaic arrays much more cost effective and not just that, much more effective. So the whole idea is batteries, which right now are very expensive, but the prices are going to be decreasing, at least that's certainly the projections, have different possibilities. There's some different possibilities of adding batteries. And as I'm assuming almost everyone here knows, and there's other ways to store energy. In the US, and I would assume all countries, we generate electricity to match the usage of electricity. As the demand goes up and down, the generation goes up and down. There isn't large-scale storage. If there could be large-scale storage, then there would be benefits, including my talk today. So types of batteries that possibly could be used, different efficiencies, different costs. And probably, I don't know if it's true for every technology, but costs are anticipated to decrease. So today's talk is this paper, 2019. This is in the journal Renewable Energy by myself, Xhou, Stamatis, and Dunbar Birnie from our material science department. So this is May 2019, so not even quite yet. We're working on the extension to that. So our research objective is a simulation-based optimization model, where the goal is to meet the demand for electricity during the outage periods over some time horizon, some planning time horizon. And some sensitivity analysis, which is interesting, but not, probably won't have time to talk, but very important then is finding this trade-off between battery price and VOLL, value of lost load. So this means the cost when electricity is not being supplied and demand is not met. So in a manufacturing facility versus a hospital versus a school, you would have different values. So first, we live in a country, thank goodness, where an outage of the grid is pretty uncommon. In fact, if we wake up or go to school and there's no electricity, it's something we talk about because it happens so infrequently. So the first issue is how often do we lose electricity, and for how long? And there's about 1 to 2 events each year. And the events last, although certainly we have a distribution with a tail, but they last different durations. It's kind of monotonically decreasing, like a log normal distribution. But the average duration might be 200 minutes or so. Now you might say, that's not very much. A couple per year, 200 minutes. But, and my student prepared this slide, he's trying to be melodramatic. He's trying to say, are these numbers small? Well, not if you're in the hospital, but not just that. If you're in a manufacturing facility and you lose production, 1 or 2 times a year for 200 minutes is a lot. That's a major economic loss. So yes, it doesn't happen too often, but it happens too much. So if there is a grid outage, the issue becomes, island mode. Can we operate, whether it be as a microgrid or can we operate independent from the power grid? So that would be islanding mode. So our problem description, we have the PV arrays. Now there could be other forms of energy. The person who asked us, the engineer to ask us to work on this, was specifically dealing with assets, I think hospitals and other things, with PV arrays. So our talk today pertains to that. But our problem description is to use the PV together with the battery. And then the issue is in terms of our optimization model, given especially batteries are expensive, how to match them to form an economical, cost-effective solution. So definitions from our paper: total system cost. We're using a 20-year planning horizon. We have the battery cost that takes place at the beginning, although my student, Stamatis, is expanding this such that its decisions can be made anywhere throughout the planning horizon. We have two parameters that you'll hear in my presentation. Loss of load probability, LOLP. We have an outage. We discretize time into hours. And for each hour, we've met the demand or we have not. It's not partial meeting of demand. We've met the demand or not. And we can have a loss of load probability hour by hour or over the whole outage duration, which is a random time. The loss of load probability, chance constraint probability. I can constrain loss of load probability to be less than or equal to a some amount, but the loss of load probability, or the estimate of it for a single outage, is a random variable. Therefore, if I want to constrain a random variable to be less than a certain amount, like 10%, I can't say for sure, so I use a chance constraint. The probability, the loss of load probability for random outage is less than a certain amount, is greater than or equal to some probability. That's my chance constrained probability. The probability that I can meet a minimum requirement for loss of load probability. Solar irradiation demand. We use actual data from some location in Long Island in New York State. Capacity, the size of the battery. You're not going to remember these, but when we get to the key ports in my formulation, I'll remind you of them. Some important ones, particularly though: battery capacity, BR, battery price, B. When these show up in the slides, I'll remind you of them. Also very important, the demand at time t. Time has been discretized. P of t, good. T of t down here. The power generated by the PV array. Outages are random events. Year K, I have a set of outages. The set is NK. In any outage, the time periods affected by that outage is a set of time periods. That's this set. And we'll get to these as they're important. So the first issue is outages. So these are some of the ones I talked about. So let's first on this. This is a set, NK, a set of outages in year K. 1, 2, 3, like that. First outage, second outage. There might be 0, might be the null set for a particular year K. Within each year K, I have the set of time intervals for each outage J. So year K, outage 1, these hours were affected, etc. TJK is the duration of the Jth grid outage for year K. So there's a random set, there's a random set, there's a random variable. So in a particular year K, I then need to sum over all the outages within that set, and that will give me the overall. For my planning horizon for K years, I sum over that. Now, the hours that demand was not met. The set O represents the hours while there was an outage. So in some of those hours, we can meet demand through the PV array, married with the battery, and in some we cannot. So we create a delta function. Year K, outage J, hour I, time has been discretized. The delta function is either a 0 or a 1. Delta T is 1 for 1 hour. And the battery, if it's reduced to a minimum of Bm, that's not 0, cannot then meet the demand. There has to be some minimum storage within that battery. But it's simply 0, 1, the amount previously stored, the amount of energy produced by the solar array, minus the demand in that particular hour. And if it's less than the min, we have an outage 1. And then, so the cumulative outage time, the lost load, but then I'm summing over all k years. So this is the number of outages in a year. Outages are random. This is the model we used. For the electrical distribution, it's kind of interesting from an industrial engineering perspective. My personal feeling is that IEs can contribute to energy very effectively. Because what is many of these energy planning problems, resiliency, is how do we use existing assets or resources optimally and efficiently to meet some demand. So it's naturally some optimization model. However, if you work with people in the distribution industry, they use terms like this: CATIE, safety. These are the people who are actually fixing the equipment. CATIE, I always struggle with this, but if you focus in on the fourth letter, duration, frequency. So CATIE, oh, good, I have it up here, because I was stumbling over what it stands for. Customer average interruption duration frequency. This is the data that the power utilities have to supply to the government. CATIE, safety. So we use that in our simulation model. The CATIE, the duration, is the expected outage duration. NK, if you remember, is a set, the number of outages in year K. So the cardinality of the set, or the expected cardinality set, is safety. So our optimization model, we use this term, the actual numbers in some location in Long Island, as part of our simulation model to define the distributions for our parameters. My objective function in this optimization model, investment cost, and then, as I've already explained, the value of lost load. The outage duration, cumulative outage duration, given those equations I showed previously, multiplied by the value of lost load. The value of lost load is a concept most engineers have some difficulty measuring, but it's something business people, economists study, and they publish numbers. The value of lost load for different industries. Every number we used in this paper can be documented. We have a reference for it. Again, we're industrial engineers, we're modelers. We need references for these. So our objective function, the battery cost, this is the equation I had previously. If you can recall from a previous slide, the delta function, again, for that particular time, I, outage J, year K, have we met the demand or not? If it's a 1, that means we have not, so the whole demand multiplied by the duration, multiplied by the value of lost load, and we're discounting it back to time 0 to create a present value. So this is our objective function. I think I have some animations here. No. Then we have constraints. We solve this problem sometimes with the constraints and sometimes without the constraints. So we constrain the expected value of the loss of load probability. Less than or equal to some number alpha, usually 0.1. Could be anything, of course, in our model. In other words, once we become disconnected from the grid, we want the probability that we cannot meet demand to be less than 0.1. You could obviously pick another number, but you would have a more costly solution if you picked a smaller number. But this is overall for the planning horizon. For some individual outage J year K, the loss of load probability for that particular outage, or our estimate of it, I should say, is a random variable. So we want the probability that for a random outage to be less than beta, which may or may not be different than alpha, in fact probably will not be, to be some high number. Because that's a random variable. So I can't solve an optimization model with a fixed constraint on a random variable. So I've put all this together and create my optimization model. I teach optimization. I'm an industrial engineering professor. You give me a problem to solve, at some point, I usually turn it into an optimization model. That's the way I think. I think that's the way many industrial engineers do. I think, no, I have not explained all this. The objective function you've seen, I just described it. Energy production is equal to the size of the photovoltaic array multiplied by the efficiency multiplied by the solar irradiation in that hour. But we're using actual data. You could argue, and we would like to change it, perhaps improve it. But we've taken the solar irradiation for a year, hour by hour, and assuming the next year will be the same. The next year will be the same. Now, that's our model right now. We could, the minimum, this means if the battery charge is down below this amount, it cannot meet demand. And that's related to the battery capacity, depth of discharge. Now, just quickly, and let's not dwell too much. Q is the charge of the battery at this particular time. During the first hour of an outage, it's some proportion of the battery capacity. The model I'm presenting today, we're assuming the batteries are fully charged at the beginning. That's a deficiency of my model. If they are fully charged, and they could be, if the decision was made to do that, then the model I'm presenting today is accurate. But C could be a random variable, or it could be some number less than that. Often it may be charged and fully charged based on the price of electricity. So there may be economic reasons when we're connected to the power grid to sometimes use the battery, sometimes not. My model today assumes the C factor is 1. Now quickly, this isn't, well, it's actually very important, but we have 3 categories. This is the charge on the battery. This is for all time periods after the first. It can be fully charged, VR. If I'm below the minimum, then it can only go up because I'm not meeting demand. I can only produce electricity. If I'm between the minimum and fully charged, I'm both producing and using electricity until it falls into one category or the next. This is a stochastic objective function. The outages are random. We're going to solve this using simulation. How do I do the simulation? Let's see if that's the next slide. No, we're not done with our formula. So then we had the reliability constraints I showed you before. This is more formal in the delta function. The reliability constraints, I already showed you these. Loss of load probability, chance constraint probability. The probability that a random outage is less than or equal to some amount. So how am I going to solve this? The objective function is a stochastic objective function because those sets, the number of outages in a year and the number of hours in an outage are, in fact, random sets. So we make some assumptions. We assume outages can take place randomly with a uniform distribution any hour in the year. We assume a distribution for the outage duration using the expected value from the Katie data, which is reported by utilities. So we randomly select the outage time, and we have actual demand data, and we have the duration as part of our simulation where we've simulated from that distribution. And we have the solar irradiation data, the actual data. We then use that to multiply the peak function. And then because it's a simulation, we need to do this over and over again, many, many times. If there's a better way to solve this, we'd like to. We can formulate it more as some sort of stochastic problem without using simulation. We're going to continue to work on this for many years, presumably. But these show the steps which we conducted. That's basically what I said. This is what I just said. I should have waited to this slide, but starting time is uniformly distributed. It's uniformly distributed throughout the day. It can happen morning, night. For us, time is discrete, 1, 2, 3. We have a adjusted Poisson distribution. There can be, if there's an outage, we don't have any outage durations of 0, so it's adjusted by 1. We do make this assumption, battery is fully charged. Our example for the paper, we actually did many examples, but the example for the paper is the same example I'm showing to you today as a hospital on Long Island. Our first version of the paper, we had 4 different examples, 2 manufacturing facilities, a school, and a hospital, but the paper was much too long, and so we ended up just this hospital in Long Island. All value of lost loads were from a reference source. It's not for us to say what that number should be. That's for a hospital, the cost or equivalent costs associated with not having electricity. We considered array size as 200 to 10,200 battery capacity. I mean, unless you read the paper, you won't know what these references are, but all of us in industrial engineering, certainly those of us who do optimization, which I do, are a little critical to the point that we're using good numbers that can be referenced. And so certainly to the extent we could, we did that here. Every number in our simulation, we do have an associated reference. And we've made some other assumptions that you could argue with. We've assumed the starting point of the outage and the outage duration are independent. Might not be so. That's something we could look at. Okay, first slide. Now this is a very important slide. This is 3, actually 4, because there's one up here. Cumulative distribution functions. The purple one is demand. So these are CDFs. So we see the demand for electricity at this hospital is right around here, where the CDF goes from low to high. These 3 are the cumulative distribution functions for supply, for the PV assembly without the battery. They start at 0.5 because there's a 50% probability that hour where there's an outage will be at night. So we can see that these lines don't intersect, and we can see that if this system is disconnected from the power grid, the PV assembly, which is effective during regular operation, is not capable of meeting the demand for electricity, basically ever. My student, he's a great student, Stamatis, he's really doing this. He prepares a lot of these slides for me, and because he puts in slides like this. And because I'm very thankful for his support, I do take some out. Some he passes the line over what I feel comfortable presenting, but he says, this is a problem. It's because we can't. The PV it's not, the whole point is for resiliency, and this does no good. Now, as we start to add battery capacity, things change. We have 3 different array sizes. And what we're doing is we're adding battery capacity. Again, this is all for that hospital in Long Island. And along my other axes, we have the proportion of hours where we can satisfy demand. You'll see on the cost graph, at first we thought there was a problem. We started to add battery capacity for these typical array sizes, and it stayed right at 0. And we thought that was a mistake. But what's going on is, with a small battery, you're only adding cost. You're not actually, it's not sufficient to meet the demand. It's only, you'll see on a cost function, which is, I think, it only gets worse. But then it starts to increase dramatically. So these green dotted vertical lines, they're somewhat arbitrary, but we're saying it's in 3 stages. We start to see no increase, but a sharp increase, somewhat of a linear increase, and then diminishing returns, where of course the cost to add battery capacity will still be linear. So as we add battery capacity, we can start to meet the demand, because of course we're going to charge it up. And again, our model assumes it's fully charged when we are connected to the power grid, and then continue to charge it when it's daylight. This is the cost objective function. This is where I'm going to. This is what I said before. So this is a huge. This is a very big array size. But for the smaller array sizes, as you start to add capacity, the cost just goes up. But then it starts to go down. The minimum cost points here, and here, are without the reliability constraint. These are the costs that would minimize cost, would cost the battery, cut value of loss of load. We add that constraint that you want loss of load probability less than 0.1, and then the battery capacity and cost increases here, here, and here for these three array sizes. So I suppose not too surprising, if we want to have reliability in addition to minimize cost, we need, I misspoke, I said larger array size. Well, that helps too, but I meant larger battery capacity. This is the same data. This shows the proportion that we can meet the constraint on the random outage duration. And for those solutions that minimize cost, not very well, 40%. But even as we add the constraints so that overall loss of load probability is less than or equal to 0.1, for an individual outage, it's only about 70% that we will meet that. This is the overall system achieved loss of load probability. As we add battery capacity, the probability we're going to lose to not be able to meet demand gets less and less and less. This is all the same data, just presented three different ways. Without the constraint for overall loss of load probability. Now, there's going to be a slide, which is going to be one of my very last slides. I want you, I think I recreate this on the left part of that slide, or I'm not sure. But notice that if I constrain the loss of load probability to 0.1, the optimal solution puts it exactly at 0.1. So the constraint is tight, not surprising. But what you'll see towards the end, if we recreate this analysis with anticipated future lower costs, will actually not be true. We'll be able to meet that constraint and surpass that constraint. But right now, it's not surprising. I'm putting a constraint on reliability. We're going to meet that constraint and not a little bit more. We're going to do sensitivity analysis. Probably we'll go through this briefly. This is kind of a difficult one to understand, but interesting. If I'm going to make an improvement by 1%, what will the cost be? Well, this is all these numbers. I'm going to make an improvement by 1%. Let's say the loss of load probability is very good. It's in here. And if it's, say, some number, and I want to improve it by 1%, I got to pay a lot more. Green means price increase. If I'm over here, where the loss of load probability is very bad, and I want to increase it by 1%, I'm going to have to get a bigger battery. But the value of lost load improvements will more than compensate for it. So there'll actually be a cost advancement. I'm going to assume this is an error, although we're using simulation, so I'm not sure. So now, the next portion of this talk is, value of lost load. It's a number that's estimated. It can vary. Similar analysts, or different analysts, could get different measures for the same facility. Battery price is changing. So we're working on the next paper the next extension to this paper, we've created a much more rigorous model, I hope. And we're trying to explore the relationship between value of lost load and battery prices. And we're trying to create a model such that the anticipated trends in battery prices are built into our model. That's currently not the case. And I have many of these plots, and they're sometimes hard to decipher. Our original work had 4. And I think the original presentation we did, we tried to describe all 4 of these. And, it's too long, number one, and started to get very boring because there's some trends that are the same. But the hospital was just something that we demonstrated for today's talk. We did also similar analysis for a school, hotel, small office, and big office. And what really changed? Well, a lot of things, but the model was basically the same. The demand for electricity changed, the value of lost load changes. But you can get very different answers. And then our colleague in material science, he's very practical. I mean, good IEs should be practical too, right? Department chair. But sometimes we think we have more theoretical models than conceptual models. And so he says, well, the people reading this paper probably aren't going to have a hospital. And if they do have a hospital, it's going to be maybe a different size. So we scaled cost, scaled battery, and provide graphs that give a tool in these 4 general categories to select battery size for some customized demand. Trade-off between battery price and value of lost load. The cost parameters we're going to use, you'll see the parameter TSC, total system cost. This would be the cost that minimizes total system cost without considering the reliability constraint. And then, so optimal TSC is with that reliability constraint. In every example I did today, the reliability constraint is 0.1 or 10%. Could be, of course, the Indian. So my students have done many, many of these plots. Okay. The analysis I showed you earlier today was for a battery price that we looked up and the value of lost load that was documented. But in our sensitivity analysis, we considered, well, battery price is variable. Value of lost load is variable. Differently, though. Value of lost load will vary based on the application. Battery price, well, we don't know the future trends, but is going down. So some interesting results here. If batteries are very expensive, and it doesn't cost very much to have an outage, not too surprising, don't get a battery at all. And of course, we can then conduct a sensitivity analysis and see the others. Same data, just it's a little hard to visualize it this way. And we make some conclusions about this. This is the lowest TSC without the reliability constraint. So we can then, the plot's very difficult, but we can then make some conclusions about the relationship between value of lost load. I'll skip through. I have many of these plots, and I'm starting to run out of time. Now, this is the same model, but now with the constraint on reliability. So you notice we never go down to the floor. Once again, battery price, value of lost load. So battery price is high, but you notice a much more larger flat surface here. This means we're meeting the minimum requirements to satisfy the reliability constraint. If battery prices could get sufficiently low and value of lost load gets increasingly high, we're going to then get a battery larger than the minimum that will satisfy those reliability constraints, because the outage costs will be more important. So that can happen two ways. Value of lost load can be fixed and this is decreasing, and that's what we actually think is going on. Or, of course, the reverse. Same data, just, we argued. What's your opinion? Is that too confusing? Probably. So we did it this way as well. And things to notice. So, this is after the first paper was written. We researched, the different people have made predictions. The numbers we used for battery price is $162 per kilowatt hour. There's been projections that this will drop as low as 74. So we recreated the whole analysis with 74. Of course, we have an optimization model. We can use it for any set of variables. And this is, I don't know, in one sense, the most valuable plot of my talk, if there's any. As battery price goes down, it's not a big surprise. We can afford larger batteries, so there's no surprise here. So the minimum overall cost, assuming both value of lost load and battery, it takes place at a larger value, and that's obvious actually. But then this is the plot that's more interesting. So now this is the battery capacity versus the achieved overall system loss of load probability. If we want to this is the data I already showed you. If we want to minimize cost, we have battery capacities here. If we want to minimize cost and also meet the reliability requirement, our battery capacities up here. And then this is the best good news in this. If battery prices actually decrease to the projected amount, we can get a larger battery capacity such that we can meet the reliability constraint, but where the minimization of total cost takes place, it actually surpasses that, which means finally we're at a point, based on all the numbers we've used in our model, and we can find perhaps some criticisms with that, in the projected future, where the integration of batteries with a PV assembly for a system like that will truly be cost effective and meet requirements for reliability. And we say resiliency in this paper because the whole idea is demand for electricity is met while power is being restored. So the system becomes resilient. Again. All right. Again, he's a good student. He's feeling to be heard if I took some of these things out. But he's saying, oh, that's good. Those are good results. So conclusions, we developed the model. This is the first paper I've ever done in this domain. It's been published. It's gotten a good reception so far. We have two or at least two more extensions of this plan. We can see the effect of the declining battery prices. It shows we can make the systems both resilient and economically viable. And this provides a decision-making tool to provide for a resilient system that's resilient in the island mode. Here's how we're going to extend this model. It's already a stochastic model with variability. We want to analyze some of that stochastic behavior more, make the model better. Demand and solar irradiation. Our current model, I've already stated this, we have a year's worth of data for demand, a year's worth of data for solar irradiation. We treat those as deterministic numbers. They're hour by hour, but we assume they repeat themselves over and over. So in practice, the demand's a random variable, and the solar irradiation is a random variable. So, that's something we've spent a lot of time argued on. And so we want to relax some additional assumptions. We want to, again, have transfer of the price of photovoltaic array costs and operation and maintenance costs. We're also assuming in this, and this is something, my main research for many years has been reliability. We're actually assuming, though, the power grid, the PV array and the battery don't fail randomly while this is taking place. Again, that's something we need to consider as well. So that concludes my talk. Thank you.
Questions?
Yes, sir.
So I know that you said that you were going to maybe in the future consider O&M, but it seems to me that battery aging and degradation might actually play quite a bit into this. If batteries have to get replaced every 5 to 7 years, say like in your car or in your cell phone, I mean, I'm not aware of a type of battery that doesn't have a relatively finite life. What are your plans to incorporate?
Yeah, and also one thing I'm learning from our new faculty member, as batteries age, they don't fully charge up again.
Yeah, their capacity goes down.
Yeah, their capacity goes down. And as I just said, batteries fail. So the one student, I can't pronounce his last name. You got anybody from Greece here? Okay, so I could say anything. No one knows wrong. Stamatis. To me, they sound the same, but he corrects me when I say it wrong. That's exactly our plan. We want this to be a decision-making over a planning horizon where we're going to replace the battery multiple times, multiple time periods. We want this to show, that's his dissertation plans going forward. Instead of making this a one-time, we can also choose not to get a battery right now and decide to do it in the future, as demand is changing. So how will this change the model? I don't know. Probably make batteries less attractive. But that's something that we want to look out, absolutely plan to do for the next few years. All these extensions, when they're no longer there, including battery reliability, and battery replacement, and battery installation, not right now, but maybe at a deferred time in the future, or we want to include in the model. But this creates a really tough model that we're not sure how to solve.
I think some batteries also self-discharge. They require to keep them topped up, some energy.
Yeah, but of course when it's connected to the grid, we can do that. But then this analysis is, strictly when it's disconnected from the grid, can we make it to the next time power is restored. So,
Thank you.
yes, sir.
I have some questions related to your recommendation. We go to that page.
That is-
Position. Yes. So here you're using multi-objective organization. So does matters involving non-matter different terms?
I'm going to argue we are not. I mean, we have, I think you're calling it multi-objective because I have cost now and costs, and I have a battery cost now, and then I have outages in the future. So I think the way you meant the question is I have multiple objectives. But I'm going to argue, no, I'm not. I'm going to say that, discounting the costs, future costs, year by year, back to time zero, and with the value of lost load numbers. So I'm saying this is present value cost plus present value cost. So at least the point I'm trying to make is I'm not doing that because, I've written a lot of papers on multi-objective optimization, and I'm very sensitive to apples plus oranges don't equal.
Well, that's one thing.
Yeah.
But the units, of course, the same.
Yes.
But my point would be, it's possible one of the terms dominates.
Yeah, sure. Yeah, absolutely. Yeah, so it becomes like the other one goes away.
Yeah, basically, another one doesn't matter.
Yeah, absolutely. In fact, we saw it. There was portions of the graph of 2 dimensions where I was sitting along the, I guess it would be the z-axis, and that's what was going on. This portion of it was not important compared to this portion. So it said, don't buy a battery.
Yeah, okay.
You know, and then it's a slight digression, but the very first paper we wrote in electrical generation optimization is in the journal EPSR, Electric System Power Research. And my student Hatice Tekiner, now a professor in Turkey, I'll bet she worked a whole year on our optimization model until we got even one result. It was an optimization model. Our objectives were minimize cost, minimize CO2 emissions, minimize NOx, NOx emissions. And we waited a whole year. I said, let's say all we cared about was minimizing CO2 emissions. Let it run. She says, you might not want to publish these results. We're never going to generate electricity.
So another question, photo on this formulation. So you were talking about stochastic optimization. So what kind of software are you using?
Simulation, right now, simulation based.
Not simulation based. So what software you're writing your own code?
MATLAB.
Oh, not I see.
Where are you solving this brute force right now? We have simulation for this, and the reliability constraints which are on the next slide. So what we're going to do moving forward as the optimization problem gets further, we're going to go to use these derivative-free optimization. You know, I forget the names of them. Black box optimization tools.
So right now you're using gradient-based method?
Right now what'd you say, gradient? No way.
Yeah, right.
We can't take derivative. Number one is stochastic.
Yeah, I know.
So black box means not derivative. Right now we're just doing numerical systems. But as we move forward, I forget the names of them, but there's several free black box derivative-free optimization tools we're going to use. You know, the quasi-gradient. You know, by exploration of the region, they estimate what a gradient would be, and then you move in that direction.
So each optimization problem, like how long it takes CPU time?
I don't know. We certainly have versions of this where the students tell me they can't solve it. So I don't know. I didn't ask. I don't know.
So I'm going to hold questions there because I know we're running a little bit long, but I'm sure that David would be happy to stay for a few minutes. If people have additional questions, we'll let people come up. But I know other people may have other commitments they need to get to since we're running a little bit past noon. So we'll thank David once again.